Yes, sir.
Okay, hello everyone, and welcome to this online webinar to highlight a quick overview of reservoir simulation. I'm Hisham Mukhtar Ali, Senior Reservoir Engineer from Cairo, Egypt. So, in this webinar, this practical session, actually, we will highlight an overview of and applications of reservoir simulation. Then the principle and mechanism of the simulator, the data required to generate or to build or to define a reservoir simulation case, the differences between the development strategy, history strategy, and prediction strategy, and so on, and then the workflow for practical applications for that simulation case using industry standard software. So starting directly with our agenda in this session, starting with an overview of the simulation, the applications of and the principles of multi-phase flow, considering the fluid modeling, relative mobility, and capillary pressure applications, and then the process of model initialization. What does it mean by initialization, and how to perform the initialization process and the data required for that process, and then how to define a development strategy and as an input to the simulation case, and within next with the simulation case study. The recovery process actually is slightly complicated. As you can see, we have multiple parameters or several parameters are controlling how much oil and gas can be recovered, and what is the expected recovery factor, and so on. Several parameters, as you can see, some of them related to the reservoir parameters, rock and fluid interactions, the ability to displace oil or gas throughout the porous media, and also the connections between wells and the reservoir, which is the main terminal or the main exit of reservoir fluids from the media through well completion. And then we have other parameters related to the sweep efficiency and vertical and horizontal mobility of the reservoir, aerial and vertical sweep efficiency. Other physical or commercial constraints are also controlling the oil recovered, or the ultimate oil recovery, like the aquifer influx or aquifer strength, the productivity and injectivity of the reservoir, also the maximum or the control of the produced ratios, like water oil ratio or gas oil ratio, and so on. Also, the maximum capacity of the processing and transportation facilities, license terms and conditions, so on. So we have combination of reservoir parameters, fluid parameters, reservoir sweep and fluid rock interactions, and also physical and commercial constraints. All of them are controlling the oil recovery process. So simply you throw out a 3D reservoir simulation model, you can integrate all of these parameters in a single 3D model and run the model to predict and to identify the possible performance of your reservoir under different development strategies. This is simply the mechanism of the reservoir simulation. So, as you can see, the reservoir system, we have two major elements considering a reservoir rock and fluids and the characterization of them. The fluids, as you can see, are typically flowing throughout the porous medium, So in a reservoir simulation model or a 3D model, we have to consider, we have to define the fluid model, considering the hydrocarbon composition, hydrocarbon or oil and gas properties, like the oil formation volume factor, oil density, oil viscosity, and so on. Also, water properties. This is regarding fluids. Regarding rocks, we have very important properties, basic properties to define or to characterize the rock, the storativity and transmissibility of the rock, fluid saturation, also fluid rock interactions like relative permeability, capillary pressures, and so on. All of these details can be considered in the defined 3D grid or 3D model of your reservoir. Simply, we have two different techniques in terms of dimensions for reservoir characterization. Zero dimensions, typically like the material balance or the um, the classical reservoir engineering tool, or the using the 1D, 0D, zero dimensional model or tank model. 1D model like the fractional flow or Buckley leverage models for the immiscible displacement process. 2D models like the early reservoir simulation models, and also the pressure transient analysis models. And mostly we have the 3D models, considering the modern numerical reservoir simulation models, as you can see. So the reservoir simulation, simply it's an numerical approach for the reservoir characterization and performance evaluation, simply by subdivision of the reservoir into a large or a specific number of grid blocks or grid cells, as you can see. The simulation equations, simply they are partial differential equations, are solved to calculate pressures and flow for every grid block at each time step for the simulator. Simply, major applications of simulation is to match all the historical performance and predict the future performance under unlimited number of development strategies and unlimited number of reservoir depletion scenarios or reservoir depletion strategies, and evaluate the performance at the simulator before applying that strategy at the field scale. The main data required to build a 3D simulation model is the structural information, the structural modeling, fault modeling, the structural maps, the elevation, the net gross rock properties, like basic properties like the porosity, permeability, directional permeability in X and Y and Z direction. Also, fluid saturation for every grid block, and fluid properties. Also, well data or well completion, well trajectory are also required, and also the historical production data and operating constraints. This is generally the data required. The principles for this is the mass balance to solve the simulation equation across one grid block or one grid cell. Darcy's law is used to characterize the fluid flow across the porous media. BVT model is also required to characterize the fluid properties like the oil density, oil viscosity, and so on, versus pressure, because the with time, we have a reduction or depletion of the average reservoir pressure, and also a change or reduction of pressure from the bottom hole pressure or average reservoir pressure to bottom hole pressure and to wellhead pressure and so on. And last principle required is the well inflow model or the IBR model to characterize the fluid behavior from at the sand face at the interface between the reservoir and the bottom of the well across the well completion. This is the major elements for fluid characterization and rock characterization, and also geological modeling to build a 3D reservoir model, considering the fluid description data, fluid properties versus pressure, and considering for the rock the basic rock properties, fluid rock interactions, and also for the geological model or the 3D model, we have to define the structural model model of facies distribution, and layering zonation and layering of the reservoir, the positional environment, reservoir continuity, and reservoir quality. This is the major three elements for an integrated model. So you can identify key reservoir features. You can calculate volumetrics like the original hydrocarbon in place, and monitor performance. Accordingly, you can take proper reservoir management decisions. So reservoir simulation, as mentioned, is an integrated tool or integrated engine to run all sources of data. As you can see, data from geology or 3D model, structure model, data from petrophysics, the property model, and properties distribution like porosity distribution, saturation distribution, and so on. Also, reservoir engineering data like the BVT and core data, as you can see. Also, production data and well compilation and so on. All of them are integrated in a single model, and then you can run simulator to get the reservoir performance and predict the future performance. Keep in mind, the simulator is just an tool or an engine, but you have to consider the analytical thinking for all inputs and outputs from the simulator. But generally, the simulator or reservoir simulation as an numerical tool is a perfect or optimum tool for the development planning for 3D visualization of the reservoir, also for well planning and volumetric calculations, the seismic modeling, and so on. So the philosophy or the mechanism of reservoir simulation, as you can see, so we have to generate a specific reservoir realization or scenario, considering all data as mentioned, data from the reservoir architecture or reservoir structure, considering the structure mapping, the fault modeling, the zonation and layering, and so on. Flow properties or petrophysical parameters, saturations of fluids, the well completion data, fluid rock interactions like the relative mobility and capillary pressure data, reservoir parameters like aquifer strength, aquifer volume, the also the structure, fault modeling, and fluid contacts, and so on. So this is representing an single reservoir realization. Then we have to define a specific development strategy, which means uh, for this realization, we have to define a specific strategy or development option to define how many wells will be or can be drilled, how what are the well controls and production controls, the different sources, the rig capability, and so on. This is the defining a development strategy. The resultant, as you can see, will be a specific simulation case by the combination of a reservoir realization and a development strategy. So the typical workflow is the data collection and analysis. All data, as mentioned before, must be considered and must be quality checked, starting from the structure and fault model. Following the structural framework is to build the 3D grid and how many grids, the grid dimensions, reservoir zonation, and the layering, and so on. So this is the at this step we have a geological model or static model representing the field before any dynamic data. Fishes model is to distribute the different rock units or reservoir hydraulic units across the 3D model. Property model is the to define the properties across the 3D model. At minimum, we have to define the velocity distribution and saturation distribution, and also fishes. After that, we can start to define the dynamic model by incorporating the dynamic data and the initialization parameters to after definition of BVT and rock physics function. So you can finally get the a dynamic case, and you can run history matching. So this is the, as mentioned, all data must be considered from the borehole seismic or geophysical data or seismic cube, the logging data, core BVT data, and so on, to define the large scale structure and fine model, and then the coarse model, and finally get simulation results. So simply you will subdivide the reservoir into grid blocks or grid cells, and you have to define basic properties for each grid block or grid cell. And next, you have to solve the simulation equations across the 3D model at every time step. This is the mechanism of the simulation engine after the definition of the 3D model. So from a structure contour map like this, we can define a corresponding 3D grid or 3D structure by considering the fault model and the pillar gridding process, the definition of grid blocks, grid dimensions, zonation, layering, and so on. And next is to define the basic properties across all of these 3D grids, like net gross porosity, mobility, and also initial water saturation. So this is the all of these data, mostly the engineering in data to define the rock properties for Fisher's model and property model. considering all the physical data, velocity mobility, relative mobility, and capillary pressure to define the minimum and the maximum fluid saturation for each phase, and also to define the initial distribution of water across the 3D model using the capillary pressure data and saturation height modeling. So simply we have this is the geological model or 3D model, 3D grid can be converted to corresponding simulation model. And the next step is after the definition of dynamic parameters and production data or measured data, the history matching, which is two-way communication process for model adjustment and fine-tuning of the model parameters. Once the model is matching the historical data, the model can be used for prediction to define different scenarios or strategies for optimum development strategy to reduce operating cost and increase the ultimate recovery. So the mechanism of the simulator actually using the grid model and grid geometry and properties, the simulator will calculate both volume for each grid block, transmissibility, and also non-neighbor connection between different grid, one grid block and surrounding grids, using the what we call the BVT model and the rock physics function to define the fluid description, the flow behavior. The simulator can initialize the model to define initial pressure and saturation distribution across the 3D grids and calculate the in-place volume, well and production data, well trajectory, production and injection data can be used to define well models and calculate flow rates and the pressure while running simulation. So simply we have discretization or subdivision in space and time to subdivide the model into 3D grids, and in time we have a specific time step, solve simulation equations, which are nonlinear equations due to the reservoir complexity and nonlinear fluid behavior. So this is the one of the examples of simulation results. As mentioned, the pressure, fluid saturation, and the fluid composition, and also for prediction the future performance of the reservoir and several development strategies. The applications of fluid data or fluid modeling, as you can see, is to describe the phase behavior and the composition of the fluids versus pressure, and also to calculate the density for each phase for the initialization process, and also the mass balance equation, because simply the one of the basic principles for solving the simulation equation is to apply the mass balance equation. The scale or rock physics function, they are required to define the transition zone between the free oil and free water zones, and also to define minimum and maximum saturation for each phase at each for every grid block. So this is the major sources of BVT data, but for compositional simulation we can apply what we call the equation of a state model, but alternatively can apply a simple BVT table to define properties against pressure. This is just a comparison between black oil simulation and compositional simulation. Simply, let's consider this generic phase behavior or phase diagram. So, this is the bubble point curve, this is the dew point curve, critical point here. So, we can use black oil simulation on this region highlighted here, on this region, which means we have mostly black oil or dead oil system, or we have dry gas or maybe wet gas system. Black oil simulation means the oil and gas phases will be represented by single or one component. But we have to define what we call RS, so how much gas is dissolved in liquid, and RV, how much liquid can be vaporized, condensed from this vapor. Alternatively, for near critical fluids like the volatile oil systems or gas condensate system, the compositional simulation can be applied, which means the oil and gas phases will be represented by multi-component or mixture, which means we have different components across the liquid phase and different components throughout the vapor phase. So for the multi-phase flow, as you can see across the both media, this is the importance of the rock physics functions like relative permeability to define the relative movement for each phase at every saturation, and to define the saturation and the minimum maximum saturation for each phase at the initialization process. So model initialization means is to define the initial pressure and saturation distribution across the 3D model, as you can see. So the widely used technique is the initialization by equilibration. This is simply by definition of the fluid contacts, as you can see, like oil-water contact at this depth, and the definition of the PVT model and rock physics functions. So the fluid contact is simply identified by the integrating of the petrophysical parameters and the pressure data, as you can see, to define the free water level or the oil water contact by considering the fluid gradient for the oil phase and water phase. The intersection is mostly the oil water contact. This is the integration between the physical parameter and the pressure data to define the possible depths of the oil water contact, as you can see from this log and pressure data. So once we define the fluid contacts like gas oil contact and oil water contact, the simulator can calculate the capillary pressure between the gas and oil phase, and also the water and oil and water phase, using this simple equation. So using this line representing the gas pressure line, and this line oil pressure line and water pressure line, the simulator can calculate the capillary pressure. So at any depth, the simulator can calculate the pressure using these pressure lines. So we have gas zone right here, and oil zone, free oil zone, which means oil plus SWI or reducible water saturation, and here we have free water zone. But the problem is the saturation distribution across the transition zone between the oil and water zone right here, and also the transition zone between gas and the oil zone. So just the saturation functions, as you can see, must be applied. Saturation functions mean they are relationships against water saturation, like the capillary pressure curve, KRO and KRW against water saturation. So these endpoints will be used to calculate the initial saturation for each phase in each grid block. And this relative mobility curve for water and oil will be used to calculate the mobility, fluid mobility, and solve the simulation equations. But for the capillary pressure, it will be used to calculate the initial water saturation across the transition zone. So the calculation, the saturation of the other phases can be calculated. So this is the simply the applications of capillary pressure data, integrating with physical parameters, pressure data, and using the definition of this capillary pressure curve, so we can calculate the across this transition zone. We can calculate the corresponding water saturation, because the saturation here is we have free oil zone, which means oil plus SWI, but here we have 100% water, and this is the level of water table. So the thickness of the transition zone and the saturation calculation is controlled and calculated by the capillary pressure data, and also the endpoints and relative mobility. This is the definition of saturation functions, as you can see, all of them against water saturation. So we typically use the drainage capillary pressure curve during the model initialization process. This curve like this. So you can define the saturation corresponding to every capillary pressure calculated by the simulator, as mentioned before. And using the relative mobility, we can define the endpoints and minimum and maximum saturation for each phase. This is the rock physics in the simulation terminology. As you can see, it's a combination of capillary pressure, relative mobility, and rock compaction. This is the rock physics function. So next step, based on the saturation functions, so we, as mentioned, the capillary pressure, so we can, for the gas oil relative mobility and oil water relative mobility, so we can define the minimum water saturation, and also minimum water saturation across the gas zone. And so the problem, as mentioned, will be the saturation across the transition zone, which is not defined. Simply using the capillary pressure, using these two equations, the simulator will apply the lookup tables to get the saturation corresponding to the calculated capillary pressure, so we can define the initial fluid distribution across the transition zone. So this is an example of the defined contact set, oil water contact and gas oil contact here, and this is the applied the saturation functions these two tables for relative mobility and capillary pressure. So say we have this grid cell in the oil zone. This is the water saturation. As you can see, it's this is the minimum water saturation defined by this table, which is 0.2. So if you look at this grid cell, for example, we have the water saturation is 0.2, which is SWI at the maximum capillary pressure. But for the transition zone, this zone actually, the water saturation is can to be defined directly, but using the rock physics and functions and the fluid parameters. So the water saturation is 0.28 right here. And for the water zone, the water saturation is 100%. So the issue, while initialization is to define the fluid distribution across this transition zone. So this is just an highlighting between the or comparison between the history matching or history strategy and prediction strategy. So history strategy or history matching is used to validate or fine-tune the model against the historical data, which means the observed or the measured data will be used as well-controlled data, and also well events will be applied. So this is the workflow for the more after model generation and running the model. So you can solve for flow rates and pressure, and run sensitivity to identify the most uncertain parameters. Accordingly, you can fine-tune or modify these most or the uncertain parameters to improve the matching of your model. Once the model is matching, you can run prediction. You can apply prediction runs for the performance evaluation. So practically setting up a simulation run or simulation case, we have to define a development strategy, which means you have to define start and end date of your simulation run or your development strategy. And you have to define wells and well rates and also constraints. Second step is to define a simulation case, which means you have to select a specific 3D grid, select 3D or define the 3D grid properties, and select the simulator options. So setting up a simulation run, at the beginning, you have to define a 3D grid corresponding to specific grid properties input to the simulator. Second step is the rock physics function. As you can see, simply the fluid context, the BVT data or BVT model, and rock physics functions. And next, the defines the strategy or maybe history of prediction strategy. And next is the to define the required simulation results or the required outputs and results of the will be calculated or computed by the simulator. Other advanced features or controls can also adjusted and customized before running your simulation run. So we will highlight this all of these details in the case we have right here. So we have this model, as you can see. So very quickly, the data of the model will be sorted or will be stored in different folders, as you can see. In this input pan, we have the different folders defining wells and all corresponding data like the global well logs, well completion data, observed data, and also the well types for maybe injectors or producers and so on. All of these details will be stored in the wells folder. Other important folders must be available to define a simulation case. The fluid folder. Fluid folder, as you can see, is it's related to the fluid definition and the fluid model, and also the initial conditions. So let's look at the fluid model we have right here from this model. So we have this fluid model. So simply in this tab, we have right here the fluids and or fluid model. Let me skip this. And you can display the fluid model data or properties in the function window like this. So the fluid model, as mentioned before, it's related to the basic properties of the fluid against pressure, mostly oil formation volume factor, the oil viscosity against the pressure. Solution gas oil ratio is defined as a straight line like this. Defining the bubble point pressure at different gas oil ratio, and also the contact set or the oil level of the oil water contact and gas oil contact. This is to define the initial conditions. Second important folder must be applied is the rock physics function, as you can see. Rock physics is it's related to the, as mentioned, as you can see, it's related to the relative mobility data, and also just the and also the capillary pressure data. So you can display rock physics function from this option. So this is the applied rock physics functions. As you can see, it's simply a combination of capillary pressure and the relative mobility data, and also rock compaction. Another data must be defined related to the formation tops, so stratigraphy, the also the development strategies folder. So your development strategy will be stored in this folder. As you can see, it can be history strategy or prediction strategy. Your model will be defined in this pan or models pan. As you can see, we have a specific 3D grid. Below this grid, we have a detailed description related to the skeleton and the fault model. As you can see, to define the your fault model, the edges of the reservoir or the 3D grid, and the basic grid properties, as you can see, like for example in this 3D grid, we have right here, this is the for example we have porosity, this is the permeability distribution. So simply can apply this option. So for the mobility distribution, let's apply the yes. So this is the permeability distribution across the model. And we have set of injectors and producers, and this is the permeability in K direction, this is the permeability in X direction or I direction. Simply you can check the dimensions of the model, as you can see from this option. So this is the model parameters or model description, the number of grid blocks or grid cells in all directions, total number of grid cells right here, and the basic properties defined in the model, like the porosity mobility in I direction, J and K direction, and the statistical parameters like the minimum, maximum, mean value, standard deviation, variance, and so on. And also you can check the distribution for a specific parameter, for example, like porosity. This is the porosity distribution across the model. So you can identify the basic parameters and statistical data of this property. Similarly, for permeability in I direction, permeability in X direction. So this is the distribution of permeability. As you can see, you can customize the scale of this property, say like this. So as you know, it means we have uni bimodal system. We have two major peaks representing two major system of the reservoir, low permeability and high permeability um, patterns. The permeability in J direction and also phases distribution across the model can be highlighted like this. So we have three major types of phases: the flood background flood plane, the channel sand, and the levee sand, and so on. So this is the defined. This model actually, as mentioned, um, will be applied, will be generated after several steps after the definition of the structure, the fault model, and the pillar gridding process to define grid dimensions, the dimensions of the grid in X and Y direction, and also the zonation and layering of the model. As you can see, this dimension is also can be controlled to define a coarse or a fine scale model. Also the layering process, the thickness and the height of each grid block can be assigned in the model generation process. After that, the model parameters or property modeling must be applied to have distribution of properties across the model. As you can see, for example, the mobility of or even porosity across the model. This is simply defined by the data at every well, and then the different physical modeling techniques can be applied to distribute a specific property across the entire 3D grid. So after that, we will import the historical data. We will define the wells and as you can see, we have set of wells right here. Let's hide this 3D grid. So this is the wells we have and the corresponding well completion. So the well trajectory, well completion data, and also the well production or even injection data. All of them must be defined. Also, the well logs, global well logs data, all of them must be defined for every well. Next step is to define a specific development strategy. So the definition of the development strategy, just loading the well log data, as you can see. So the next step is to define a development strategy. Yes. So this is the wells, and highlighted in the green color. This is the well completion interval. So all of them can be controlled and defined across the wells folder. So global well logs, global completion and observed data, and the classifications of well for by injectors, producers, gas producer, gas injectors, and so on. So next step is to define a specific development strategy. So the development strategy, as you can see at the beginning, you have to select the simulator. So we have basic two basic types: black oil or compositional simulators, or advanced simulator, covering all applications of black oil or compositional modeling. And select the strategy type, is it history strategy or prediction strategy. And for the history strategy, as mentioned, the well data and also the well observed data must be defined in this rule or keyword, which is history rate control. The observed data, as you can see, must be defined, and the also the history pressure limit for the producers. After the definition of the history strategy, the next step is to define an simulation case. So in simulation, you can define a case, or and can edit an existing case. As you can see, let's say for this case, we have this already applied case. So define simulation case is applied across this window, as you can see. So at the beginning, you have to select the simulator and the type of the model. For conventional applications or classical applications, single prosody system will be applied, unless you have a dual prosody or dual mobility system like fractured carbonate reservoirs. Next is to define the 3D grid, and we have major steps to define a simulation case, as you can see. After the definition of model description and any comments related to the model, next is to define the in the grid tab. As you can see, you have to define the basic grid parameters, the minimum parameters. You have to define porosity, which is the um, basic parameter to define the storage capacity of the reservoir, and also the permeability, which is to define the capability of the rock to transmit fluids in all directions in I and J and K directions. Mostly mobility in the horizontal mobility or mobility in I and J directions, mostly equivalent, but in the vertical direction, it's mostly less than the horizontal mobility, unless you have highly fractured system with vertical fractures to contribute to increase the vertical permeability. Next is other parameters like the fault transmissibility, network growth, and so on. Several parameters can be defined to the grid itself. After that, we have to define the BVT and rock physics function. So as you can see in BVT and rock physics functions, we have to define, as you can see, drainage rock physics function, which is the drainage capillary pressure and relative permeability data defined from the inputs. Also the BVT model and the corresponding initial conditions for model initialization as mentioned, and also rock compaction. Next step is to define the strategy. As mentioned, strategy can be a history strategy for history matching or prediction strategy. And for the strategy, the corresponding start and end date must be assigned from the previous step, corresponding the development strategy. And we have other advanced options right here. And for this tab, we have several advanced options related to the advanced grid system, runtime options of the simulator, how the simulation results will be loaded after the end of simulation run, or after a specific time, like check for results every specific minutes, or load results after the end of the run entirely. This is the runtime options. Other options related to sector modeling, transmissibility, and partial export. And also you can check the keyword editor for the simulation engine itself. Last step is to define the required simulation results for the summary vectors, or the line plots, like XY plots. This is the what are the required properties or required results and the for the after the end of the simulation run for the group, or for wells, or even for the entire field. This is the selected simulation results as summary vectors, pressures, flow rates, also ratios. All of them are required. Initial 3D grid properties you can select from this option, and recurrent 3D grid properties, as you can see. Let's select another case like this. So for this case, for example, we have recurrent 3D grid properties. This is the selected properties. This is the properties regenerated for the 3D grid after the end of simulation run, and also the print file, the reporting frequency, all of them. for the recurrent 3D grid properties, you can generate these properties every one report step. So we have in reservoir simulation, we have what we call simulation time step. This is the period of or length of time the simulation engine, for example, Eclipse and other or whatever the engine, or even maybe Eclipse 100, 300 even per sec. So this the time the engine will solve the simulation equations for every grid block. This is the length of time the this equation will be solved. But the report step, this is the step or the length of time the simulator will submit the simulation results. This is the difference between the time step and a report step, which means it will submit results or generate a report for the results. After setting all of these parameters, and select the required simulation results, you can check you can apply and check the consistency of data, and check if there are any errors of in the data and so on. And finally, you can run your model. Once you click run, as you can see, so the simulation, the simulator or the engine will start to run. What does it mean by running the simulator? It means the simulation will start to solve, as you can see, the simulation equations for each time step at every at every time step for every grid block in your model. So once the simulation completed, so the data will simulation results will be automatically uploaded as mentioned, because we selected to load results at the end of simulation. Now click OK. You can display your results, but at the before that, let me yes. So we have this window to display your results. As you can see, it's like an align plots or an XY plot, as you can see. So you can, if you click right here in this tab, so we can customize the sources of data, the displayed properties, and also all of the results required. So we can select which case simulation from the sources, and so simply we have several cases. The first case applied or performed case number 1, and after specific modifications, while the history matching, we have the case underscore history matching. These two cases will be compared against the observed data right here. The data will be displayed for specific primary identifiers. So you can display the data on the field level or group level or even well level, which means the data will be displayed for each well separately. Next is to define the required properties, which data you need to display. The data right here are stored in also in different folders. as you can see, data related to cumulatives or cumulative production and injection, data related to pressure like bottom of pressure and so on, data related to flow rates for oil, water, even gas, or even water injection rate. Ratios like the oil ratios can be calculated like gas oil ratio, oil water ratio, water cut, and so on. Other properties can be displayed as well. Once you select the data, you can display here the data for every well. So as you can see, we have in the red color, this is the data of case number one, and in the brown color, we have the final case of history matching. Two cases are compared against the observed data in the green color. Simply, this plot is fully customized. Everything can be customized, like the line style, line thickness, as you can see, line type. All of these customizations can be applied. Also, the data itself, the unit system can be changed from the metric unit field unit, as you can see. So this is the data of the first case to the last case after modification of some model parameters. Simply, the changed parameters to achieve history matching like this, as you can see. This is one, it's another well. This is the next well, as you can see. This is a water injector. And this is the performance of another injector. So, and this another producer. So, what are the major parameters are changed to achieve improvement in the history matching? At the beginning, the relative mobility data is slightly changed. This is the initial relative mobility curve in the blue color, and in this in the green color, and in the blue color we have, this is the data using the history matching. So we have a slight a change in the relative mobilities, considering the endpoints are the same. SW critical can be slightly changed, and also the relative mobility to water and oil, and also can be changing, and history matching parameter. Also, another parameter is changed to achieve history matching in this model, is to changing the mobility in the vertical direction. So if you back to the model here, we have change in the mobility in the vertical direction using a specific multiplier to achieve the history matching. Simply the selection of parameters to be applied, to be changed or modified during the history matching. This is simply following the process of what we call the uncertainty and optimization or sensitivity analysis. So I will not highlight this step due to the time limit of this webinar, but I will highlight another important issue right here, is the volume or volumetric calculations. So let's check this case, which is case underscore history matching, what we have right here, what we call the print file of this simulation case, as you can see. So in the print file, you will find, as you can see, all details of this run. As you can see, the keywords and model parameters and the PVT data, grid data, and so on. But what we need to highlight here from this file, we have right here in this section. So we need to check the calculated. Yes, and in this section we have this calculations field totals. This is the calculated in-place volume for the model. It's almost, as you can see, 486 million cubic meter. This is the estimated in-place volume, and this is the calculated, as you can see, average pressure in bar, and this is the bore volume, and this is the currently in place and originally in place. It's almost five, as you can see, it's 541 million cubic meter. So we have another process here is for the volume calculation. So simply click here in this option for reserves volume calculations. So volume calculation, this is another technique to calculate volumes by what we call the volumetric equation, but using the 3D grid. So we have defined the fluid contact, oil water contact used in this. Let's display the model. Say this is the mobility distribution, as you can see. And let's display the float contacts. This is the level of the oil water contact highlighted in the blue color. So for the volume calculations, we have to define the hydrocarbon intervals, and also you have to define the general parameters like velocity and net growth. Velocity is used from the 3D model. For the oil zone, we have to define the water saturation and also the oil saturation. So water saturation can be extracted from the model or the 3D grid, and also the oil formation volume factor. This is also can be generated from the 3D grid. For the gas zone, similarly, you can take the similar parameters from the 3D grid. This is regarding the properties. And next is to define the required calculations, and you can calculate the volumetrics for even every rock type or every feature in your model. Once you finalize this, you can click run to display your volumetric calculation results. So for any questions, please keep it at the end of the session. So this is the this is the also this the story calculated from this step. We have slightly some differences between the initialization calculations and volumetric calculations due to the technique of the volume calculations and especially at the grid cells at the oil water contact, how the volume is calculated. This this is regarding the details of volume calculation of the volume for every step, and this is the results of as mentioned of the volume, and you can calculate volumes for every segment, as you can see, and also we can calculate volumes for every zone. So you can check the major contribution for each zone, and this will be the target of the field development and so on. So this is the one another application. Finally, I will highlight in this session one of the advanced options can be displayed especially for water injection operations. If you have a 3D model applying, and we have set of injectors and reducers. So we can display the streamlines like this. So streamlines, so we have one injector right here, and we have other injectors, another injector here. So injector is defined by, well, I2, I3 right here, but the producer we have B4 and B3 and so on. So this is the this streamlines is an good features to highlight or to display the contribution between or the communication between water injectors and the surrounding or the corresponding oil producers, which can injectors showing high contribution to which producers and so on by running the streamlines, as you can see. So using this option for the time player, so you can run. So you can display the change of the this these streamlines and the change of saturation across the streamlines, as you can see. So in the blue color, we have this is the 100% water. This the we have the legend color scale is the regarding the water saturation, and here water saturation at the highest zone of the grid block. As you can see, it shows the minimum water saturation, but here we have one. This is the major injector. We have another injector right here. Also, we have another injector in the other side of the grid cell or grid block right here, this one. We have another well right here, this one. So this is the one of the features can be applied to visualize your reservoir. Another features like let's display the 3D grid and hide these streamlines. Once to display another important visualization feature. For example, the let's display this property as porosity. We have several, as you can see, several visualization features to display the to display your 3D grid and understand the properties across the 3D grid. So you can take slices of your 3D grid in any direction, as you can see, even in I or J or even K direction. So this is another slice of your model in the K direction, in K direction, in J direction, and this one in the K direction. So this is important visualization tools and features to understand and to take a closer look of your reservoir and understand the communication between wells and communication between different fault blocks and so on. This simply this well we have the completion interval. So the reservoir simulation at the end showing powerful integration capability between all disciplines, showing a powerful visualization and the evaluation tools for reservoir characterization and reservoir management, and also the performance prediction. That's all I have, and this is the end of this session. Thank you so much for doing this session, and feel free to ask any questions